So as we start 1.4, let me first let you know that in section 1.4, we do have a written work piece to it. Okay, so this will be for Friday. You'll do the written work piece. Let me flip it over here so that for those who aren't with us today and they're just recording this later, it's on page 83, and it's only 2 problems. It's 96 and 97. Okay, so it's not very long. It will not take you long. Just 2 problems. But that's the written work part of it that we'll do in this section. All right, so let's get started. We are looking at this section at continuity and one-sided limits. We've already talked a little bit about one-sided limits, but we've only talked about one-sided limits from a graphical perspective and a numerical perspective. So what we're really going to look at in this section is one-sided limits from an algebraic perspective. Okay, so this is actually talking about continuity as well. Continuity: a function is continuous at a point C, when the following are true. The first one is that the f of c is defined, right? So from a graphical point, that meant there was a solid filled in dot and not just an open circle. It meant that there's not an asymptote. Okay, so we can't have an asymptote or just an empty circle. The second one, the limit exists. So we actually can't have any jumps happening either for it to be continuous. No jumps is what that's really eliminating. And it eliminates asymptotes as well, but asymptotes were already eliminated by the first one. And then the third one is that the one-sided, or the limit and the function values both exist. And what that does is it eliminates this happening, where there's a hole in the graph. It actually exists because it's a solid piece, and the one-sided limits, both of them exist, right? So the limit exists, but they don't match. So this cannot happen. This is a no from the last piece. So intuitively, you know what it means to be continuous. You probably have something in your mind that says something like this. It means I can draw it without picking up my pencil. Right? And that's not a bad intuitive idea. This is simply a little bit more strict in its definitions, but it has the same feel to it when it's actually applied. This was talking about continuity at a specific point, right? The point C. This is talking about continuity on an interval. So a function is continuous on an open interval when it's continuous at every point in the interval. That seems reasonable. A function that's continuous on the entire number line from negative infinity to infinity is called continuous everywhere. You'll also hear the phrase sometimes continuous on its domain, right? So it simply means that all the x values that exist, it's continuous at those x values. So it's a little bit less than the infinity to negative infinity business. Like, it doesn't give you that, because you could have like an asymptote or something like that too, and it's still continuous on its domain. But continuous on its domain is another phrase that we'll see pop up from time to time. Now here's the cool thing. When we're looking at one-sided limits, algebraically, it is irrelevant that it has that plus or the minus after it. We treat it just like it's not there. So this says, find the limit if it exists. If it does not exist, explain why. It wants the limit as x approaches 8 from the right of 1 over x plus 8. And we approach it and we deal with it just like that plus after the 8 is not there. And we evaluate it by plugging in x equal 8. And as long as I get a numerical value, that is the answer. So again, just like we wished it would be. Now, on number 2, we run into something that we've seen happen already. If I try to plug in the 9, again, the negative after it doesn't make it a negative 9, it means from the left-hand side. But if I try to just plug in the number 9, what happens here? Yeah, I get a 0 over 0. So what we expect and what we think happens here is that there's a hole in the graph, right? That somehow I've got the ability, like I did in the last section, to factor something and eliminate something. And I see radicals. Agreed? Okay, this is exactly where we left off on last time. This idea of radicals and what do I do with them? Because I don't have my traditional factoring techniques at play when there's radicals involved. So do you remember what we did to try to eliminate that radical? We rationalized. Nick, can you tell me what I'm going to multiply by on top and bottom? Fabulous. Radical x plus 3. Okay, that's called the conjugate. And again, the reason we like it is because the inner and the outer terms add to 0. Elisa?
Can you not factor out the bottom and do square root of x plus or minus 3?
So yes and no. It sometimes will work, and for this one, if you think about it that way, you can. But you have to be a little bit more careful, and I'm not sure that you quite even caught exactly the pieces there. But I think you'll catch it once we see it, and then you'll know what to do. So hold tight to that idea. It's not a bad idea. Okay, we're going to multiply out the numerators. So I get an x when I multiply first terms, and I get a minus 9 at the last terms, right? Okay, is that all of them? Now, in the denominator, you still see I have that x minus 9. I do not want to distribute through the denominator. That is typically not helpful when I'm rationalizing things. So don't try and, sort of clean up the denominator. You really want it to be in factored form. And so we like this because what happens to my x minus 9s? They cancel out. And that's what was causing my problem, right, was the x minus 9, because I'm trying to plug in 9. And when I try to plug in 9 to x minus 9, I get 0. So notice again, I mentioned it last time and I'll mention it here again, I keep writing limit until I put the 9 in. Okay, now I have 1 over, I have the square root of x plus 3. All right, can I put in a 9 now? Yes. Awesome. So now I have the ability to plug the 9 in. And I will get 1/6. Any questions on that?
That it could be negative, and then it'd be 1 over 0.
Oh, okay, so that's a good question. I'm glad you asked it. Okay, so Elisa's concern is the fact that we've got a square root, and when we have square roots, then the square root of like 9 and the square root can be 3, and the square root of 9 can be negative 3. Everybody remember that? Okay, so here's the deal. If I have, and you can write yourself a note, if there's a square root already in the problem, this is called a principal root. Principal root. And it's always positive. The only time I have to worry about the plus and minus on a radical is if I've inserted the radical into the problem, which I did not. The radical was already there to start with. So that's a little bit of a caveat because we do have to worry about it sometimes, but when it's actually given to us, it's definitionally speaking only the positive part. Thank you for noticing that. I didn't think to mention it. All right, let's do one more and then we'll call it a day. Sound good? Okay. Last one for today. When I plug in or try to plug in a 0 into this, what do I see? 0 over 0. And this one is not quite like anything we've seen so far. Agreed? Yeah. Partly because there's an absolute value involved, right? I haven't done anything with absolute values yet. So I'd like to talk a little bit about what happens when I have absolute values. Because when I have absolute values, it does matter if the value is coming from the left or the right. At least if I'm approaching 0, which this one is. I'm approaching 0 from the left, correct? So what is this telling you about x? Is negative, you betcha. It is negative. So I don't know if you've heard of absolute value or seen absolute value defined quite the way I'm going to show you, but the absolute value of x has a dual definition, or a piecewise definition is what we usually hear it called. The absolute value of x is x when x is greater than or equal to 0, but the absolute value is the opposite of x when x is less than 0. Now, that doesn't mean that the absolute value becomes negative. But what it does mean is the absolute value causes the sign to change, right? What's the absolute value of negative 5? It's 5. Well, we don't have a mathematical way to say remove the 5. So what we do instead is we say, okay, well, what it really is it's the opposite of negative 5, right? This is the x value that was already there, and I want the opposite of it. Feels a little uncomfortable. Just set in that right now. It's going to be a little uncomfortable, but it's okay. So what that means is because I'm coming at 0 from the left, this absolute value of x on the numerator is actually equal to the opposite of the x value. And the denominator is equal to the x value because it already was. So what's going to happen to my x's? They cancel. So what is negative x divided by x? It's negative 1. This is just negative 1 now. Now, if you think about it, it should make sense. Let's just try a couple values, like from an algebraic perspective, or even maybe from a numerical perspective is more what I'm really doing. What if I used x equal negative 1? Okay, if it's negative 1 on top and I take the absolute value of negative 1 is 1, but the denominator is negative 1. So 1 divided by negative 1 would give me negative 1. How about let's just do like negative 10, not because it's close, but because it's a different value. If I have absolute value of negative 10 on top, what's the absolute value of negative 10? 10, but I have negative 10 on bottom. What's 10 divided by negative 10? Negative 1. And I don't know if you know how to graph in your calculator with absolute values. You don't really need to. It's not super important life skill or anything. But if you were to do so, you would actually find that this function looks like this. And so it would have an open circle right here and a closed-in circle right here. And the reason it would is because this one is the equals and this one is the not equals, right? It's the strictly less than. And so if we were approaching from a graphical perspective, I did it from a numerical perspective sort of out loud. From the graphical perspective, we're on a constant value of x equal negative 1. Okay? So absolute values are a little weird, but they come into play every now and then. And again, the only time this matters is if x is approaching 0 from the left. If the absolute value is x approaches 1 from the left, it wouldn't make any difference, right? Because 1's a positive number, and even if I'm approaching 1 from the left, I'm at positive numbers, 0.9, 0.99, 0.999, they're all positive, and the absolute value wouldn't make any difference at all. It mattered because it was approaching x equals 0 from the left. All right, so we will stop there today. You've got homework from 1.3 in WebAssign. 1.4 is open, and you know that there's going to be a 1.4 written work and WebAssign on Friday. Also, as a reminder, there's a quiz review questions posted inside of Canvas. If you didn't have an opportunity to do those last time as you were preparing for your quiz, and your quiz wasn't quite what you'd hoped it would be, might be a good idea to check those out this time. All right, I don't collect them, but they're for your benefit if you want to explore those options. Have a great day, guys.